Thanks, Jim, for inviting me for that and for coming to speak to you all today. My name is Fobs, spelled FBZ. That's what I go by because my other name is very long and doesn't work in a lot of cultural contexts. So, yeah, I go by Fobs. I'm a hardware hacker, reverse engineer, and mathematician. And I also happen to like textiles a whole bunch. Yeah. In case you're rushing to take pictures of links, this is all the links in the entire talk. So both this slide and the slide at the very end, if you take a picture of this link has all the links in the entire talk. So I'll pause here for a second and say a few words. Yeah, I live in Seattle currently, and it's been wonderful to come out and collaborate with the folks here at CMU. I have a different brand knitting machine that they have, and I'll get into that a little bit. Did everyone get a chance to take a picture? If not, you have a chance at the very end. So a little bit about what knitting is. Knitting is a series of loops connected to the previous series of loops that have a directionality associated with them. And a knitting machine has a series of these hooks. So mine has 699 of these on the front bed and 699 on the back that pull a loop through the previous loop. But you have to think of this as lined up with a whole bunch of them all next to each other. I got into knitting machines with this project in 2010, which is where I met Nadia as well, at Mediamatic in Amsterdam, where we built a top scroller video game that output the winner's panel in knitting, and we did it in 5 days. So we took an existing consumer knitting machine from the 1980s and modified it with both hardware and software. This is my reverse engineering notes from that workshop. And added new connections, new hardware, and added various systems to make it work with modern computers and make it scriptable. And in the process, we also made row and column matrix control board that is open source as well. So if you have any kind of button matrix that you want to push programmatically, we've got you. This is open source hardware. You can slam it on there. It's not just for knitting machines. This worked pretty well. We had a fun challenge to make an interface where you created an avatar, you played a game, and then if you won, it was knit as a panel that showed out the front window of the display space. And that's kind of how I got hooked. So fast forward to, so that was in 2010. Fast forward to 2016, this is me looking like a grinning, very happy person. So that's my knitting machine that I have, and when I say I crowdfunded it, so thank you, backers. But it is owned by me. So I'm not part of a lab, I'm not in academia, I'm an indie producer of textiles, and I have full access to my machine, which was my big issue. So it's a CMS 530 HP 7.2 gauge industrial knitting machine made by Stoll, which is to say it's a pretty standard industrial flat knitting machine. So most knit production around the world either happens on a Stoll or a Shima. They have a Shima here at CMU. So you have one of those two brands because together the brands have something like 90% of the industrial flat knitting market. So chances are if you're wearing something that was commercially produced, it was either produced on a Stoll or a Shima. I have a big space, which I feel very lucky about after visiting the space here and realizing how space is so limited in an academic context that it feels nice to have a lot of room to be able to work on things. I'm also part of an art collective in Seattle that owns a 5,000-pound rated forklift, which is how I chose them. So, because otherwise I wouldn't have been able to get my machine off the truck without hiring riggers. And largely for the last 4 years, I've been knitting things like these generative cellular automata scarves. I knit a series of 800 one-offs for a Kickstarter, which I don't necessarily recommend doing crowdfunding. You can talk to me about this later if you want to know why. But every single scarf in the collection was one-off, and each scarf shipped with the specific source code to generate it to the consumer. So the leftmost scarf and the rest of the scarves are all different from each other, and they ship with their correct source code as well. What I'm releasing today is I'm actually releasing all the code for generating imagery in all of my products that haven't already been released. So this is the new hotness. I've decided I don't really want to be doing a whole lot of consumer products in the future, and I'm trying to veer off into weird and strange directions. So if anyone wants to produce consumer products, have at it. The code's up, and feel free. I get a lot of demand for a lot of these products over and over again, and I don't necessarily want to be the one who fulfills it. And it's interesting to note that I went to manufacturers and tried to have a run of 500 one-off scarves in the same dimensions, the same yarn, but just unique images. And every manufacturer that I talked to said, well, it'll cost you the same to do one or 5,000, so 5,000 times 500 is your cost. So, yeah. Have fun. Here you go. Yeah, it's got lots of code comments because this ships to end consumers. So I want people to play with the code when they get an item. Outputting things such as Mandelbrot fractal scarves. This one. Can hand this one around. And silly things like this cyber scarf that just says cyber all over it, except it's also fully reversible because I interleaved it with mirrored versions. So it's kind of hard to read on this. This is the type of image that goes to the machine, but here's a kind of a split out image so you can see how I designed it so that you always have an end of the scarf that looks good. I mean, obviously you'll have an end of the scarf that looks good in mirror selfies, but this way it looks good even if you don't have mirror selfies. Here it is coming out of the machine. I released this on Cyber Monday. This is the kind of products I like. So have fun. Make all those products that I'm kind of done making. I wanted to talk a little bit about finishing details. So when you knit a double bed jacquard, this is the style of knitting that I've largely been doing, but I would like to not be limited to in the future. Means that you can't completely mimic you can have an exact equivalence of the bind on to the cast off. So here's a sewn, hand done tubular bind off. This is before I had an industrial machine. This is done on a hacked consumer machine. And what I've done for my products is try to mimic the bind off so it looks as much like the tubular cast on as possible. So the one that I'm passing around has that example. So see, if you're a knitter, try to see which side is the tubular end and which side is the bind-off end. I think they look pretty similar. They're both very rounded and maybe don't show so much of the difference. Another thing to note is that when you're doing double bed jacquard and you have long areas of one color along an edge, so here you have a big patch of gray that comes up to this edge, you have to seal that edge, otherwise the edge of the knitting will be open. So you have to choose which color is the sealing color. So you can see along the patch of yellow there's actually a line of gray. And that line of gray is what is sealing it shut because I've decided that the gray is the dominant color. This works for the reversal, obviously, but you do have to choose and kind of put a 1 pixel border all the way around things to make them seal in. And then some other design options mean that you don't have to seal it in. So if you have a lot of color changes along the edge, so for example, along this edge of this macrom scarf, these are a series of scarves that I did along with code from Trammell Hudson that are just visual representations of boot ROMs from vintage Macintosh computers that were all on archive.org. This is Apple II. So it's a slice of the Apple II, but it wraps natively in the length of the scarf. So if you hold it and offset it, the track actually wraps properly because I'm pedantic. So If you have color changes that happen a lot, you don't really need to seal along the edge and you can kind of fake it, but you kind of need to look for the dominant color of the top side of the scarf. So here I've chosen in this particular scarf that white is the dominant color because I do have this big patch of white along one edge, so that's the color I choose to seal. So if there is any black that comes up to the edge on the front side of this scarf, it will actually be unsealed from the back. But I've decided design-wise it's okay.
Why are these all two-color?
So knitting has a property that two-color double bed jacquard is fully reversible. And with an item like a scarf, I don't want there to be a wrong way to wear the scarf. And I don't want to have to sew them together. So when you buy sports scarves, so like the scarves where you're like, yeah, go team, those are actually knit flat with kind of a back, and that back is sewn on the inside. So I kind of wanted to get away from that paradigm and make things that have better drape, so they have better kind of a loose, flowy quality to the fabric themselves. And that's why I've chosen to go with two-color double bed jacquard for a lot of these, because they're scarves. If you have something like a sweater, you can hide the ugly part on the inside. So the other things that I think about is directionality when it comes to generative design. So this is the Rule 110 from the Elementary Cellular Automata, which is a 1D cellular automata. A lot of you may recognize this because this one has been proven to be Turing complete. It's the only one of the rules that has been proven by Matt Cook. Great math paper if you're into it. Math, computer science, crossover paper, I would say. So what's cool is that I kind of think about the directionality so that the points of the triangles are accented with the direction of the knitting, because knitting is actually little V's. It's not little square or rectangular pixels. And so because of those V's, I try to accent the points of Rule 110 with the point of the V. So I knit it in a specific direction, so bottom up, so that the points of the knit stitches accentuate those triangles. And then some other rules that also are very pointy, like Rule 90. So Rule 90 also has the property that it is Sierpinski triangles if you start it with one pixel in the starting row.
What are the boundary conditions?
What are the generating row conditions? Oh yes, so I didn't talk about that in this talk, but I largely do things that have a wall. So there's 3 ways to generate elementary cellular automata: with walls, where it just has a dead pixel at the side, as a tube where each edge affects the other edge, or as a triangle that goes out forever and ever. So I generate with walls. So yeah, and one of the properties of that means I get a 1 pixel border all the way around the edge, which means with double bed jacquard, I don't have to worry about sealing the edge. So I just thought it was more elegant that way, to not have to fake it and cut out a slice and then knit that slice. I want the slice that is there to be exactly 1-to-1 with the code, because I think it's more elegant that way. So yeah, Sierpinski triangles, if you only generate with 1 pixel in the starting row, this has a whole bunch. This has like 5 pixels in the starting row. This one only has 1. So Rule 90, I also knit bottom up to accentuate those triangles, but then some of the rules have kind of a square-like structure, such as Rule 41, and I knit that top down to accentuate the straight line. So again, knitting is a little V. So on one edge of the V, you have 2 points, and on the other end, you have 1 point. And the edges with the 2 points can accentuate that flat line that you're trying to show. It can accentuate that flat line that you're trying to show much better if it's knit in the other direction from the pointy rules. So those are just some design considerations that I like to take into account when doing generative work on industrial knitting machines. Another book that I'm super obsessed with is The Algorithmic Beauty of Seashells by Hans Meinert. It was out of print, it's back in print, which is exciting. And what it is has models of seashell patterns in algorithms, and so this is Symbiola vespertilio, the bat volute, and so you have a way to model the pattern that happens on the edge of the shell as it grows. And I did a series of knits with these before I got my industrial machine. And what's interesting is that you can there are random factors in it. So they are reproducible, so they are discrete algorithms, but you can have different outputs even with the same starting row. I was really interested in the 3-color rules, and I couldn't really knit them until I got access to industrial knitting machines, so that was one of the things I did once I got access to my own machine was be able to knit them. There's a few issues with the code, the way that it comes with the book. So this is kind of what 3-color knitting looks like on the back. There's different ways you can do those infills. This is a checkerboard infill, but it's not one-to-one. You can't have the back be the opposite of the front. So you can have 2 colors per row and have it be fully reversible. The issues with this are the jaggediness. So it's not pixel native to the dimensions that I'm trying to knit, and therefore I have a lot of approximations and we get these kind of weird artifacts. But wonderfully, there's someone else who's super into this book, namely Francesco de Comite, who has been working on rewriting all the algorithms from the book in Python to be able to 3D print seashells with the colors printed as well. And so he and I are hopefully going to collaborate in the future, and we'll have some native to the pixel environment stuff. So what we worked on this week, I just wanted to touch on a little bit. I was grouped with Mark Gillespie, Jenny Lynn, and Ella Moore, and we ended up doing 2 different projects, which you can see out in the poster session. I really wanted to do weird things with cables, and I'm glad some people came along with me for the ride this week. We tried knitting a square with an arbitrary knitting direction. I'm just going to check the time real fast. Do you want me to try to stop at my original stopping time? Okay. So knitting a square with an arbitrary knitting direction is not super trivial. You're actually starting on 2 edges instead of starting on one face of a square and going to the other one. You're starting on 2 faces using short rows to navigate to the opposite 2 faces. So it sounds easy, but in knitting this is actually not a super easy thing unless you have access to code where you can generate things like this. So we ended up being able to knit cables with procedurally placed cable crossings, but at arbitrary angles. And we could also angle in the other direction. I don't have that picture here, but it's out in the hall. So this allows you to do all different kinds of weird structures that were not open to us before this week. And I would love to be able to continue this and try to make some full-sized examples that don't necessarily have to be sellable products, but that are like wonderful, weird clothes with arbitrary knitting angles that also include cables. We also worked on cables that go across a straight background. So the cables are moving, the background itself is not. Again, with the same group. And it sounds very easy, but once you start adding a lot of things together, things can break down pretty quickly. So we have cables traveling across the background, and they're attracting and repelling each other. And what's cool about that is that if we can generate that onto a sweater form, then we can have these fun, like generative sweaters that have fun cables that go across them. So you're probably sensing a theme. I really like things that you can wear, things that seem like a mundane piece of clothing, but I want clothing that's interesting. And I know a lot of people in this group are working on more theoretical aspects of knitting and knitting machines, but I really like things that sound as boring as a sweater. So I'm looking forward to continuing some of this work and collaborating. What was really cool is Knit Out that Jim and the team here have been working on, which is a way to control industrial knitting machines, and it turns out we'll also probably be able to control my brand of knitting machine, not just the Shima that is here. So I look forward to like continuing that work, and I especially appreciate that there's a front-end Python version of it. Yeah, it was really cool working with the group this week, so thanks, group. What was neat is being able to use Git and software collaboration tools for quickly throwing together things and iterating on examples the whole week. It's the future I had dreamed of, and I feel really lucky to be able to have come and experience that this week. I'm also interested in weird structures that don't necessarily lend themselves to products, like can you create a Mobius elementary cellular automata scarf? And I thought of some ways of generating it, but we ended up finding a different way and published a paper about it last year. So this is an academic math paper from the Bridges Conference last year that I'm a co-author on, where we generate a Mobius cellular automata scarf. I have one example with me, but I'm not going to pass it around because it has raw ends. So when you do the half twist and you connect it back to itself, the cellular automata continues. So it lines up perfectly, but it's not bound off. So if I hand it out, it might unravel and I would be sad. So you're welcome to come and look at it and talk to me about it. This is the Rule 105 example, because we also had a Rule 150 example. How am I on time? 5 minutes? Okay. So there's a great talk about it, so you can see my two co-authors talk about it during the conference last year. We have a novel way of mirroring the cellular automata across the center to be able to create these Mobius structures. And we found some weird properties. And one of those weird properties is that the loops for Rule 105 and 150 seem to have the same cycle length, and then we find the exact same loop every time we run the algorithm. So we don't have unique loops at a specific scarf width. We have one cycle, and those cycles tend to be close to powers of 2. And so we were kind of mystified about this. And we produced, these objects to be able to knit, and we thought, oh, that's cool. We made this weird thing, but this is probably not a huge space. And we still had some open questions. But now we have answers to those questions, because my next door neighbor actually wrote a follow-up paper, my actual next door neighbor. So he got nerd sniped into this because I was talking to him about my paper, and he's also not an academic mathematician. He actually works in industry and cryptography, but he found a way to blow open the project space, and this is an unpublished paper by Ross Snyder. So he comes at it from cryptographer's way, where he has used matrix mathematics to break down the problem, and he shows that we only found a teeny tiny part of the number of possibilities of the loops for some reason. And so these are the number of generations that you find at different length with 114 wrapped Mobius scarves. So you can see we have log base 2 number of solutions. So we have a lot of solutions, so lots of different loops at these marks that are 73 apart. So because and he breaks down in the paper why these certain intervals, why the coefficients make it so that there's a lot more variation. And he also shows us why we were getting things that were close to powers of 2. So if you have a visualization that maps the seed generation to cell value, these kind of straight black bars, these vertical ones, those are near powers of 2. So yeah, this is, it's not yet published, but if you want a copy of it, just let me know, I'll email it to you. He also has a whole bunch of Python tools that he wrote for it, and I haven't had a chance to knit any of them yet, but we have a much larger output space. We thought we had one loop in a scarfable length, but we have tens of thousands. So that's pretty exciting. I'm probably not going to knit tens of thousands of scarves from that series, but it's always fun to see what things can happen. So as closing thoughts, I just wanted to put it out there that manufacturers kind of impose limitations on production and speed, and this is kind of an unusual example because usually the numbers of colors per row on commercially produced double-bed jacquard, which is the type of structure that I'm handing around, is 3, because most people have 3 system machines, which means you can do 3 operations per pass, and so most manufacturers limit themselves to 3 colors per row, but this actually has 4 colors per row, so you can see that dark green, white, gold, and the red are all in the same row. So this is kind of an unusual example that was produced. This is also 4 colors per row, so it's kind of an unusual example. Could be that they had a 4-system machine, but they're not as common, so maybe. The other thing that manufacturers do is that they limit things to a very specific type of yarn. So you see almost everything is in acrylic because it's very reproducible, and acrylic is actually very friendly in a knitting machine, and it's also cheap, and it's also abundant in the form that you need it for an industrial knitting machine. That means coned, properly tensioned on the cone, in big cones so you don't have to swap the cones as much. So there's a lot of limitations that happen in manufacturing that don't necessarily need to be limitations if we're indie manufacturers. If we're, a person with a machine, or, a couple of people with a machine, have much fewer limitations than what is actually being produced in out in the world commercially. I thought it also might be nice to highlight this LaTeX knitting package by Ariel Barton. So it is a way to, with text, generate charts for cables. So this could be used for visualization if you're already doing software-generated knits that you want to put, that you're trying to knit on your industrial knitting machine, but you need a visualization in between to be able to see, are those cables going the way I think they are, and have a pre-visualization before you knit it out. The other thing which would be cool is to be able to not only target, with knit out, not only target industrial knitting machines or consumer knitting machines or prosumer knitting machines like the Knitterate, but maybe you could also output hand knitting instructions. And what could be cool is that not only would you output the chart, but you would output the handwritten version of the hand knitting instructions. So on this side, where it says P2CR3R, that's purl 2, cable right 3, cable 3 right, cable right 3 left. And those are all standardized hand knitting text. And the chart is also a standardized hand knitting format. So it could be cool to be able to output a lot of versions, not just things for knitting machines, but also things for hand knitters. I don't know, that was just a thought. Or maybe to be able to go in the other direction, take hand knitting instructions and be able to make them into machine knitting instructions. It would be really nice to have some more reusable functions in scripted knitting machine code, and I'm sure that's where we're headed to in the future now that we have more people that have access to an industrial knitting machine, or more people that are going to have access to a prosumer knitting machine like the Knitterate, is that we're going to be able to have these chunks of reusable code that hopefully we can use as building blocks. So things like cable kickbacks to release stress on cables, bind-ons for single and double-sided knitting, bind-offs for the same, classic cable building blocks, code that protects against common issues. Like this week we had issues where we weren't starting on the front bed on the right-hand side of the machine because we had generated code that didn't take that into account. Code that automatically flanks cables with purl stitches to make them pop. Rib tightening code that already has ways to increase tension on cuffs and collars. So this is definitely not the entire space. There's so much more to be done with tooling for scriptable patterns for industrial knitting machines. It's just like a nice, this is what popped out from this week for me. I would like to collaborate. So please take down my contact information. I'm not necessarily looking to just be your fabrication. I'm looking to collaborate with you on code. So I'm not looking to be the factory that you call to say, hey, can you make this exact thing that I want? I want to help you collaborate and get to something good. So I can code. Use me in that way. Don't necessarily use me as a manufacturer, but I would love to collaborate on weird projects, academic projects, industry projects, whatever you can think of. Yeah, let me know. Thank you.